look at this example. We talk about the liquid phase reaction. Liquid phase reaction from reactant A to B. This is internal liquid phase reaction in liquid phase. The reaction takes place in a continuous well mix 10 liters. I did talk to you already, well mix or perfect mix. Perfect mix reactor, that means concentration in the tank is uniform or equal to every point of relocation and also equal to the outlet. That means CA in the tank equal to CA out. Temperature of pressure in the tank equal to out. This is the definition of well mix. It's very important. We have the volumetric flow rate of inlet 1.15 per second and outlet also 1.1 per second. And we know the rate of reaction. This is the consumption. 0.005 C per second. The tank is initially filled with solution that contains 2 mol A per liter. This is at time equal to C. CA equal to 2.0 liter per mole per second. Mole per liter. This is the initial concentration at time equal to C. For this, we know right time equal to 0. CA equal to 2 mole. Okay, now you know flow rate in, flow rate out. You know the concentration of A in 10 mole A per liter. You don't know out. You know CA equal to CA. That means that you can calculate in terms of accumulation of in terms of outlet. But outlet equal to CA. We have 4 questions. Question 1, you have to write the gas balance on in the tank and provide the initial condition. And question 2, calculate CA at steady state. And for this case, we consider the unsteady state. If we consider steady state, what is the concentration at steady state? What is the technique to consider the steady state? How to do the topic? And the third question, sketch or plot the graph between CA and time. So what is happening when time change? What is the concentration change? Okay, the last term so far the balance. So for this case, the answer is if you contract the mass balance, you get dCA by dt is a function of CA, a function of time. How to solve this? And plot time from plot concentration. Okay, the first question you have to contract the mass balance. Mass balance equation. Have you know right dm by dt equal to m in minus m out plus j minus con. For this case, we consider A there is no consumption. Sorry. A there is no generation. What A is reactant. Yep. dm by dt accumulation equal to m in minus m out minus con. For this case, okay, for the first term, accumulation. Accumulation. For this case, you can calculate the mole of A in the reactor at any time. The mole of A in the reactor at any time is VC. VC. You know V is 10 liters. VC This is the mass of mole of A mole of divided by dm by dt equal to rho Ca by dt. Rho is constant. Volume for this case 10 is constant. 10 multiply dCA by dt mole A per second. This is accommodation. Then input equal to volumetric flow rate multiply concentration of input. Liter per second multiply mole A per liter, we get mole A per second. This is input. This output 1.15 liter per second multiply Ca, we get mole A per second. Did you know input and output? So this input is output. And generation is no, but there is clear that consumption equal to volume multiplied the rate of operation for this. This is consumption equal to 0.005 C by this by volume we get mole A per second. And now you know equation input, output, consumption. We substitute this into the general equation. We get accumulation term equal to input. This is the generation term minus output minus accumulation. Output minus accumulation. And this is the equation in terms of the mass balance of you divide this both sides by 10. So you get dCA by dt equal to 0.15 minus 0.002. 0.02. Because this equation, this term, 0.15 minus 0.05. This is the equation or ODE of the concentration of a with respect time. And now you know the time 0 at t equal to 0, concentration equal to 2 mole per liter. This is the equation that you obtain from mass balance of this is the first equation. And the second equation, at steady state, at steady state, what does it at steady state? There is no accumulation. This term equal to 0. Okay, you can approximate at steady state. This term equal to 0. That's this equation equal to 0. 0 equal to 0.15 minus 0.02 Ca. Ca here is the steady state. You can solve for Ca directly. You can solve for 0 equal to 0.15 minus 0.02 Ca. For this case, Ca. Okay, the CAS is 7.5 mole. This is the concentration at steady state. At steady state. Okay. The third question. The question you plot the concentration with time. For this case, you can estimate. You can plot Ca with respect to time. For steady state, that means time approach infinity. This is the steady state. Steady state assumption, that means time approach 0. Okay. Now you know time 0 equal to 2. And also the time is infinity. Concentration is approach 7.5. This is at initial state. You can approximate like this and approximate like this. For this case, the plot, in general, you can estimate. This is the change of concentration with time. The concentration is constant with this state. This may be about 200 minutes the time the concentration with the state. This is not exact to the approximate. Okay, the last real equation. You know, this is the equation that we obtained from mass balance. And then you know initial concentration. For this case, the simple way you can find separation of water, separation of water, this is CA. Okay, you PCA equal to dt, and this term 0.15 and not 0.02 CA. For this case, you can solve by integration both sides. It should be times 0 equal to and volume. Initial volume is sorry, CA. Initial CA is 2. From 0 to any time. From 2 mole A per liter to CA. Then you can subtract. Integrate dt, we get T. We get T equal to 0. We get T. And integration this. You get 1 divided by 0.02 log 0.15 0.02 C. This integration from 2 to C. Like this. This is I think all of you can integrate. This is the knowledge for the calculus. Okay, after you take the upper and lower limit, you get time equal to log 0.15 multiplied this term. And then you get the general equation right. Log time log this, sorry. This term equal to this. And this term equal to this. And then you can express CA is a function of time. For this case, CA is term of logarithm. You can take exponential portion, you get this term equal to this. And then you can solve for CA. CA equal to this. This CA is a function of time. This is the concentration is a function of time. And also from previous, you know that this step 7 point how to convert this from this equation. At time approach infinity, it is satisfied. At time equal to infinity, this term is minus infinity approach 0. You can cancel this. Okay, for this step, it's correct. Okay, this is the general equation for concentration is a function of time. That's I form the unsteady mass balance. We get this. And then if you plot CA is a function of time. CA is a function of time. And use this equation. You substitute you can calculate A, and then you can plot A with this equation. This is the initial CA equal to 2 at time 0. And this the approach infinity. The approach infinity you get C is for 7 point. This is the example of the unsystem mass balance. Again, you have to know what is the accumulation rate, what is the input, what is output, what is the generation of consumption. Generally, the consumption I only for the exam. Okay, this is the example. Okay, the next, previously we talk about the mass balance, and then you can talk about the energy balance. For the general energy balance, you have accumulation equal to input minus output. For energy balance, we talk about the internal energy. kinetic energy and potential energy. The acceleration means energy of the system. In similar way, the mass balance. Acceleration means mass of the system. Okay, for this case, we talk about the energy of the system, kinetic energy of the system, potential energy of the system. This is term of the accumulation. Delta U, delta EJ, delta E. And then the input term. Input term. For this class, we talk about the input is equal to positive. The positive for we have the system. Input Q is positive, and outlet work is positive. Okay, for this case, input the input of energy in terms of mass input and heat input. You have to check mass input and heat input. For mass input, the energy can input to the system based on enthalpy. Enthalpy is delta PV plus internal energy. This is come from the full work as with the input in the mass. Okay, mass in multiply the energy term, enthalpy, so work and internal energy as kinetic energy as potential energy multiply the this is the input energy in the system at time which volume, and also input is at time. And the next term output. Output also similar. Output multiply entropy out, kinetic energy, potential energy, and also work. Okay. Then you substitute all of this to the general equation. You get du by after apply the limitation. The definition of limitation, you get the derivative equation. Du by dt, dek by dt, dec by dt. Equal to m in multiply free term of energy. And the enthalpy kinetic energy intensity minus them out free term of the energy. Entropy kinetic but Q minus. If there is the steady state external this equation the same as we talked about this system. But for this work, we have to include this for and steady state system. Okay, for simplify the energy balance, the system has a single input stream. If the single input stream or single output stream, maybe M in equal to M out equal to M. M equal to M out. And generally, the kinetic potential energy change in the system is without the negative. The E, A, the E, P, F, T. That means M kinetic in, kinetic out, and potential in, potential out, and potential. Generally, we can cancel the term of kinetic and potential. Then you get internal energy with respect to time equal to M multiply S in minus S at Q minus S. This is for the open system. For the closed system, there is no flow in, flow out. So this is equal to closed system. Okay, sorry. If we apply for the closed system, then we got to see only charge. But sometimes the temperature and composition of the system content do not vary with position within the system. But sometimes T out is system equal to T. This is for the perfect mix. So that involves you concentration in the reactor equal to concentration out. It's also imperfect mix on the T out equal to system equal to T in the reactor. So for the next consumption, that's like for the no phase change or chemical reaction take place within the system. For the case of no phase change, no chemical reaction, internal energy or entropy are independent of pressure. The change of internal energy, the change of entropy, not depend on pressure. Not and this means that CV or CP of the system independent of the composition. So for this case, you can use the internal energy of the system equal to M multiply U the system equal to MU reference at CVT minus T. Okay, du by dt equal to MCV by MCV dt by dt. And also S in S out, S is equal to CP T in minus T reference. S out equal to CP T out minus T reference. For this case, no phase, only the temperature change. Okay, then you can conclude for the single system, no phase change, right? Because system no phase change or reaction. For open system, you can express the energy balance in terms of this. This for open system. And for closed system, like no energy in, no energy. Get this. This for open system is 4 in, 4 out. This is closed system. This is the general equation for energy balance. Like for open system, for closed system with no phase change. Okay, we look at this example. Okay, for this case, we have a Weldmix reactor also. Weldmix reactor is a bad reactor. Bad reactor, that means there is no inlet and outlet of the reactor. Because the bad reactor, we have the initial concentration, initial magnitude. We have the heating. Sometimes we have the heating. Sometimes we kill this heating, electrical heating. Liquid reaction. The reactant is increased from 25 to 250 Celsius. We use that from 25 to 250 before reaction takes place. Okay, use this data to determine time required for heating. We would like to increase from 25 Celsius to 250 before reaction. But in case there is no reaction, because we only consider the system before reaction. Okay, we have the reactant mass is 1.5 kilogram CV. You know, reactor is the property of reactor, mass of reactor, CV of reactor, and heating rate into the system is 5,000. For this case, we have no reaction, no phase change during heating because we talk only the heating system before reaction. For reaction, the negative energy added by the thermal. But for this, we can solve there is no work. There is no work, no chemical reaction. For this case, we can look at this. For closed system, no flow in, no flow out, and no work. Okay, we get MCV dt by d time equal to Q. For this case, no reaction also. We get this equation, no reaction also. We know the initial time temperature equal to 25 Celsius. 25 Celsius. And also you know the final temperature is 250, but we don't know final time. But we get we solve for T. We solve for T. Okay. For this case, you know MCVD time by dt equal to Q. And also you can solve MCVD time equal to Q d time. MCV constant. MCV indicate from 75 Celsius more than 50 Celsius. Indicate from time 0 to TM. MCV get the temperature from 25 to equal to Q time from 0 to TM. And then MCV 250 minutes equal to QTF minus 0. And then you can find for TF equal to MCV divided by Q. MCV divided by Q. You know M. Okay, for this case, you know M. CV, you know MCV for this case. You know Q. But how to calculate CV? We have CV2, CV of wave and CV of wave. For this case, you have to calculate the average CV. From CV equal to M reactant, CV reactant divided by total. M reactor, CV reactor divided by M. And now you can see MCV equal to M reactant multiply CV reactant. Plus M reactor multiply CV reactor. You can calculate the average CV in terms of MC from the reactor and reactant. Then you know MCV equal to 7,000 minus 52 per Celsius. And then you can substitute that to this MCV and no Q. Is it the Q? And so for and then you will get time equal to 53.7 minutes. We use the time about 53.7 minutes. You can increase from 25 Celsius to 250 Celsius. This is the application of the unsteady energy balance. Because the time, the temperature is dependent on time. It is an example that we apply the energy balance with unsteady system. But the last example that we talk about it, unsteady system for energy balance. For this case, we have the engine. As I have the engine. This engine used to generate heat or energy. Inside the air in the engine housing is circulate rapidly enough. We circulate the air around this engine. Okay, we have the inlet and outlet. The flow rate of air is equal. We know the initial temperature of air 65. But we don't know the time or the temperature in this house. Like this housing. We flow the air to circulate the engine. The engine will generate heat. Okay, we generate the Q out from the engine to the housing. QJ. That QJ. For this case, heat generated 8,530 BTU per. This is the heat generated by engine. Okay, the air in the engine housing is circulated rapidly enough for its temperature to be considered uniform and equal to the temperature of the outlet. For this case, we would like to control the temperature of the housing is uniform. And also the temperature in housing equal to the temperature out. But that means we would like to control the temperature in this. It looks like the perfect mix. And this work air pass through the engine housing at the rate of 6 pounds more per minute. 6 pounds per minute. In the temperature is 65 Fahrenheit. And average to 0.2 mole of air controlled in the engine. That means we have the accumulation of air in the system is 0.2 pound more air. Like contained within the engine. And sometimes we have the heat loss from the housing. We have to heat generated by engine and heat loss from the housing to the engine. We have the engine inside housing, heat the housing, heat generated, and also heat loss to the surrounding of environment. Heat loss, this is the heat loss. In case by this situation. Okay, again, for this problem, we have two heat generated from engine. The generator is outlet from engine to the housing, and also heat loss from the housing to the environment. By this. We have the air flow through the house to control the temperature inside the house and go through the house. Okay. For this case, calculate the steady state temperature if the engine runs continuously or infinite. So that means if we approximate at time is approach infinity or very long time, what is it? Temperature. And also derive the differential equation for energy balance and so on. Okay, for the first step, if we back to the general equation, there is no phase change, there is no chemical rate, and you can apply this. But for this case, there is the open system. You can apply this equation. The first step for steady state, there is no phase. Okay. The first case we consider the steady state dt by d time approach zero. This MCP Tn minus T plus Q minus W. T in is 65. T out or T state is unknown. There is no work, no modifier. And Q should be Q gen minus Q. This is equal to Q gen minus Q. We have to Q generate from the engine and Q rod from the housing to the surrounding. Okay. MCP T in minus T. MCP T is TS steady state. At 65 Celsius. Okay, what is this? It should be MCP T minus T equal to Q dot minus. Equal to C. Okay, and then you get MCP T should be T steady state minus T in 65 Fahrenheit equal to Q. Q equal to Q gen minus Q naught. This is the Q gen. This is the Q naught from problem statement. This is Q gen. This is Q naught. Q naught is a function of time. Get this equation. Get this equation. And for this case, you can assume like the ideal cat we have here. Ideal cat we have here. And you know from the slide that I talked to you to calculate the entropy or the specific entropy C P equal to CV plus R. C equal to CV plus R. You know CV already. Plus R. And then calculate for MCP. You know CV. And then MCP. You know M is mass length, inlet. Is mass length multiply CP from this equation. You get MCP. Okay. MCP. The unknown is TS. The unknown is TS. And this also TS, not TS. Okay, we have substitute this and then solve for TS. Okay. Substitute this. If we have only 100, you can solve for TS. get T8 equal to 179 Fahrenheit. Okay, this is for the first system. If we talk about the steady state system, this term equal to 0. And then you can solve for temperature. You can get the outlet or the temperature in the house equal to 179 Fahrenheit. This is the steady state system. And this ideal because if you would like to control the temperature inlet is equal or uniform to some time, right? It's a long time. But it is the first system. And for the second system, you use the full form of the energy balance. This is not equal to 0. This is not equal to 0. You know M, you know CV. You substitute MCV from previous. MC. You know Q gen, you know Q naught. You substitute all of this into this equation. You get the differential equation. Get dt by d time equal to -74.9 temperature. And also this is you can solve this dt divided by -74.9 t minus equal to d time. And it fails from T0 to the full time 0. Okay, time at T0 at initial time to any temperature. Time 0 to any time. At time 0, temperature is equal to 65 to any temperature. And then you can solve for it. You integrate dt divided by this term and this term, we get 1 divided by -74.9 log this term. Get from 65 to temperature. You get dt, you get t. T from 0 to t. And then you get the general equation. From this case, you can express in terms of t as function of time or time as a function of temperature. But in case we will express in temperature is a function of time. The function of time. Get like temperature. Get this is okay. That is by equal to then you take exponential both sides. Exponential both sides. You get the term of equal to and if you can solve in temperature is a function of time. You get this. This is unsteady solution. Solution. You get temperature is a function of time. When time increase, the temperature will increase. The temperature will increase. Okay, look at it. When you toss temperature and time. You start from 65 because it is at time 0. T equal to 65. And also the temperature is approach to T steady state. Approach 5 seconds. Temperature approach the constant temperature at 179. But during this is the assessment. PCE show you how to solve the unassisted mass balance and also energy balance. But for this case, we have only the ODE differential equation, first order ODE differential equation, only one. If we have more than one reaction system, maybe multiple reactions, mass balance on substance A, mass balance on substance B. For that case, we talk about the system of ODE. Maybe equation 1, equation 2, equation 3, we have 3 equations of ODE. For that you have this, but you need one more initial time. One equation, you need only one initial condition. If you have 2 equations, you need 2 only differential equations, 2 initial conditions. If we have 3 equations of ODE, you need at least 3 initial conditions. This is the example that we talked to you for the unseen-state and catalytic mass and energy balance. I will give you some more example on this on the catalytic energy balance for electric system and talk to you on this day. And also I will give you one more equation, one more example for the catalytic mass and energy balance.